Okay. So I'm gonna try to go through this quickly. Because the Bills versus Chiefs game is going on, and it's halftime, and I want to get this done. This is late, by the way. Should have been done a few days ago, but we've been busy watching football this weekend. So I'm going to write out. We're gonna go through this, by the way. Yeah. So side angle side theorem. So if two sides and the included angle of one triangle is congruent to two sides and the included angle of a different triangle, then the two triangles are congruent. Dang it. I think the game just started up again. Hold on. Hold on. If the game's going on, I gotta put up the score. Dude. I gotta put it up on Google for a second. Gotta be in the loop, you know. So, to show off what this is, I'm going to make a picture for this. Guys, I'm sorry, I'm distracted. Let's call this A, B, C, and D, E, F. So what this theorem is saying is that if we have two sides that are congruent, so let's just say AB and EF have a congruent mark, and AC and DF also have a congruent mark. And if there is an angle that's sandwiched between those two, we can make the statement if the segment EF is congruent to the segment AB, if the angle F is congruent to the angle A, and if DF is congruent to AC, then triangle ABC is congruent to triangle DEF by side angle side. This is what we're saying with this. If we see the side angle side, that pattern, we can say that these two triangles are fully congruent with each other because of side angle side. Think of these theorems, these two, well, I guess we'll have another one later on, as shortcuts to proving congruency for triangles. So this is one of our shortcuts, side angle side. And remember that the angle has to be in the middle. The angle cannot be on the outside. It has to be sandwiched between those two sides. So that's side angle side. We also have side side side, which states that if three sides of a triangle are congruent to three sides of a different triangle, then the two triangles are congruent. So if I were to draw out a figure again, funny enough, these are almost the same looking triangles that I just did. Not intentional. Definitely not intentional. I'm not being sarcastic. By the way, that was a purely coincidence that I made them like that. So what this theorem is stating, just like above, we have to look at the actual figure itself. So if my segment AB is congruent to my segment EF, if BC is congruent to DE, and if AC is congruent to DF, then I can state my triangle ABC is congruent to my triangle DEF by side, side, side. This is another shortcut to proving triangle congruency. So if all my sides are congruent on both triangles, then I can say that the whole triangles itself are congruent with each other. It's a shortcut. These two are our side shortcuts that we are learning in class. But what about the other one that might be different from these two? Like having, what if we had the angle on the outside? Would that prove congruency? No, it would not. Look down at this example down here. As you can notice, we have our congruent markings on these triangles with side, side, angle, side, side, angle. But notice the key difference in why this doesn't work. Look at angle C. Angle C is very different in the fact that this angle F is definitely less than 90 degrees. And this angle C is definitely more than 90 degrees. Which means that C is not congruent to F, which proves the fact that these two triangles cannot be the same. They are not fully congruent with each other. So we could state that even though that's not even. I'm gonna have to scribble that out. Even though scribble that out. I still don't have white out here. Even though the triangles share congruent parts, that doesn't make triangle ABC congruent to triangle DEF. And I'd put a big ol' X mark in between these two because you can't have that. You can't use SSS. You're not allowed. Not allowed to use SSS. Not SSS. SSA. So I'd write down can't use SSA. Good. It's not even on. There you go. Can't use SSA. Not allowed. You cannot use SSA for proving triangle congruency. So one thing to help you to remember that, a phrase, if I would say so myself, phrase. No ass in geometry. To remember that SSS doesn't work. Or SSA doesn't work. Oh my gosh. SSA doesn't work. SSS does. If you have trouble remembering that SSA doesn't work, just remember the phrase no ass in geometry. Hopefully that will ring a bell to you guys. The only time I'll let you swear in class is for saying ass for SSA. The only time I'll let you. Let's prove some triangles. Before I get into this, since I am recording this after the fact of class time, if you are having troubles with the proofs, think of these as not proofs right now. Like, that's a bloated question, I know. But just don't think of this as a proof, per se. Think of this more as what's the final thing I need to add to my triangle in order to prove congruency? At least for this example. Because looking at this right now, there's two options I could do. I could do P and R, or I can do SQ, the line. Like that segment, or angles P and R being congruent. And that's the only way we can work with that. In 5.7, we would be able to find a way to find angle P and angle R, but we aren't on 5.7 yet. The only option we have is working with SQ and remembering the fact of reflexivity. And that's what's going to help us. Because SQ, this segment, is in both triangle PQS and triangle RQS. Which means that SQ reflexes on itself. So we can use that to our advantage for writing out our proof. So I'm going to make my table, my 2-column. You can do flowchart if you want, but I'm going to do the 2-column because that's what I did in class. So I'm going to write out my given, which was PQ is congruent to RQ. And we had PS congruent to RS. And that was given. And I wrote down already about the reflexive part, which is SQ being congruent to itself. Because SQ shows up twice in the triangle PQS. I guess I'll use blue to help with this one. And in triangle SQR, showed up twice, same segment that we're working with, which is the reflexive property that made this true. So I'd write down the reflexive property for my reason. Which, looking at what's given already, we already have the segment marks here and here. And now we have the ones down the middle, so I can conclude my statement with triangle PQS being congruent to triangle RQS. Because of side, 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 we have 3 congruent sides on 2 different triangles, so it works. We're good. Going on to example 2, we don't have as much information given to us, so it's a little harder to at least given to us like on the figure itself. So we have to actually look at what's given in order to figure out what we need to work with. So not going to write the 2-column yet. Let's look at our given to see what we can work with. The thing that I noticed right away is the fact that we have a midpoint with B being our midpoint. Oh my gosh, this yellow doesn't work. You can't see that. B is our midpoint. I'll use orange to circle that, I guess. B is the midpoint. So this is B. And remembering what midpoint does, that makes 2 congruent segments on either side. So these 2 congruent because of midpoint B. And now noticing what I have right now, and you can look back up here to help you. I have a side and then an angle because I have 2 right angles. Remember, right angles are 90 degrees. If I have 2 of them, that means both sides are 90 degrees. So we can touch upon that when we make our proof. That means the only possible way of congruency we can do is do side, angle, side. Because that's all we know. We know side, 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 and side, angle, side. So that means the side that has to be congruent is this one right here. Because that's the only other one. If we have an angle already, angle, and a side, this side has to be congruent. And remembering what we just did up here with the reflexive property, we can apply that down here with CB. And that is how we can make our proof. So I would recommend when you guys do proofs to not write the proof out right away. Don't focus on the proof. Focus more on what you need to do first in order to show everything off, I guess. Figure out how the triangles are congruent to each other. And then you would be focusing on writing out your proof. Like just how we did in the last 2 examples. We focused on how to make our triangles congruent, and then we started working on the proof. I'll switch colors for the angles. So what I just wrote down was the midpoint stuff, with B being the midpoint of the segment AD, and having that split off AD into 2 congruent parts, being AB and BD. I wrote that down in my second statement, and my reasoning was the definition of a midpoint. So for 3, our other given was the fact that angle ABC, which is this one right here, and angle DBC are right angles. And that was given. And we know that because they're both right angles, they're 90 degrees, that they would be congruent to each other. So we can say for 4, our reasoning is that all right angles are congruent. The game is on. And then to finish off the proof, bringing back down the reflexive property with CB being congruent to itself, because it shows up in both triangles. So this is the reflexive property. And that means I have concluded my statement with triangle ABC being congruent to triangle DBC, and this was SAS. And I will make a note with segment CB being in both triangles. And if you need to have that confirmation of, do I have everything for my proof, you can label everything out in your proof, showing like, hey, that's one of my sides, this is my angle, and this is my other side, showing that I have SAS, making sure that I have that already, so I'm not forgetting anything in my proof. Just take note that you have everything, I guess. Just because stuff can be lost in the sauce sometimes when you're doing stuff. Okay. All right. Oh, you guys could see my pens. All right, reminder. And this will be touched upon in 5.6. Remember your angle properties. This was Unit 3 stuff, specifically 3.2/3.3. This dealt with like alternate interior angles, vertical angles, alternate exterior, corresponding, linear pair, and consecutive interior. I would probably make a star or circle or something around alternate interior, vertical angles, and linear pair. Those ones seem to pop up the most frequently when we do proofs. So remembering how alternate interior looks, vertical angles look like, and linear pairs. And also another thing just to remember, parallel lines and transversals. Like being able to point out what is parallel and figuring out what's a transversal so you can use these properties well enough. So just keep that stuff in mind when we move forward. Like in example 3, in our case, we're going to be asked to determine if we can prove these triangles with SSS, SSS, and SAS. Being able to describe what we see. So for A, noticing what I have already for my properties, I have a side angle and a side angle, and remembering that AS is not allowed in geometry, I can say no, these triangles aren't congruent. This shows SSA. Not allowed. not allowed. B, this is why we have this up here. This one, because you'll see problems like this. Notice these arrowheads on our figure. This shows us parallel lines. This shows us that BC, the segment, is parallel to AD. And this also gives us the fact that segment CA is a transversal. We can use that information to our advantage in order to see if these triangles are congruent to each other. So one thing we can do, if this is transversal, we can look on the insides of these angles to see if there's anything that, is congruent with each other. And yes, there is. With this angle right here and this angle right here, those two are congruent. So that's good. And then with the transversal itself, it's also reflexive because it's on triangle ABC and it's on triangle ADC. The transversal is on both triangles, so I can say that it's reflexive on itself. So I'm going to write out what I'm working with right now, I guess. We found that angle BCA is congruent to angle CAD. And CA is congruent to CA. Reflexive and alternate interior. And this just makes our statement, yes, congruent by SAS. That's my concluding statement. They are congruent, so good job. And then one last thing is this one right here for C. I can say that this is congruent with each other. Again, with the reflexive property right here down the middle. JL is in this top triangle. And it's in the bottom triangle. And we have congruent sides all around with congruency on every side. Now, it shares the same congruency all around, which is okay. It can share same congruency. So I'm going to write, it's okay to have same congruency all around the figure. And I'm going to write, yes, congruent by SSS, side, 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 because we have side, side, side. And then I'm going to make the reminder down below, stating the fact that the reflexive property shows up so much. The reflexive property shows up a lot. Know how to recognize it. It will be your best friend when it comes to proof, so just be able to recognize it, and I think you guys will be okay. All right, one last thing to actually go over, which is our special case of AS that we have in geometry. In general, SSA is not a valid way to prove triangle congruency, but we do have one case of it where it does work, which is only in right triangles. Now, in order to understand this specific case, we need to actually look at the anatomy of a right triangle itself, picking out what parts are what and naming them. So I'm drawing out my right triangle right now, and I'm going to say that this part is my hypotenuse of my right triangle, and this stuff in blue are my legs of my right triangle. So that's important information to know. The legs are adjacent to the right angle. The hypotenuse is directly opposite of it. And with that, we can actually make a new statement, make our special case for the right triangle having congruency with side-side angle. So, if the hypotenuse and a leg of a right triangle is congruent to a hypotenuse. I spelled hypotenuse way wrong. Oh my god. And a leg of a different right triangle, then the two triangles are congruent. Drawing out a picture, as always. I use green for my outline. Drawing out my right angles, and I'll make my segments. Let's say right here and here. I can say that if, oh, I didn't even label it. Oops. We'll have A, B, C, D, E, F. If our segment AC is congruent to DF, if our segment BC is congruent to our segment EF, and if our angle B is congruent to our angle E, then our triangle ABC is congruent to our triangle DEF by the hypotenuse leg congruence theorem. We denote it by hypotenuse leg. Don't denote it by SSA. This is how we denote it in our proofs, and we have a proof to go along with it. Let's do it like we did before, where we didn't even outline everything. We didn't build the proof first. What am I trying to say? We didn't do the two column first. We just took notice of what's happening. So we got to prove the following statement. We have our triangles right here. Let's work it out. We do know that there are right angles, which is good because that means we are having a right triangle in this case. So we have some right angles right here, and we have some sides that are congruent. One thing that should be sticking out to you is the fact of this line in the middle of this figure. What this line is, why is this so damning of a thing in this figure? Well, it's because PR is in both of these triangles, and remembering how we have done proofs already with having a line segment cutting through both triangles, we can say the fact that PR is congruent to PR already, because it lies in both triangles. And that is what's going to pretty much finish off our case for this proof at this point. So we know already, all right, we're working with right angles, and we have two sides that are congruent. We have side angle, and since we're working with right angles in a right triangle, that means we're using hypotenuse leg. So I'm going to write HL over on the side margin. We use in this. I can now build my statement. I have all the information I need. I finished my problem already. I just need to write it in proof form. Let's build it out. I'm going to separate my given right now. So my PQ is congruent to RS, and that's given to me. And I'm going to write that angle Q and angle S are right angles. And this was also given to me. I'm also going to say that angle Q is congruent to angle S. And I know this because all right angles are congruent. And to finish off my proof, I can say that PR is congruent to PR by the reflexive property. Kansas has the ball. They're at midfield. I'm on copium right now, guys. This is no good. I can't have Kansas winning. I am a certified hater of Kansas City. They cannot win. Not allowing them. All right. Anyways, we have everything that we need. We can line out what we have, to show like, hey, it works. Like I have a side here. I have a side here. I have an angle here. It's formatted as side angle side right now in this proof, but that does not mean this is side angle side. Take a look at the figure itself. I have angle side side. It's just the ordering of it. I'm just making sure I have an angle, a side, and a side that I'm working with. But I can finish my concluding statement saying that my triangle PQR is congruent to my triangle RSP by the hypotenuse-like theorem. Good. Do these problems without even thinking of your proof first. I think that's going to help you guys the most, instead of, okay, I need to worry about building up this proof and figuring out what's happening over here. Don't worry about the proof right now. Worry about figuring out how these are congruent first, then write that in a proof. I want you to do that first. I think that's the easiest way to doing these problems, if I'm going to be completely honest. The last thing that you guys need to do is be able to recognize properties and just kind of right away, not right away, but get in the habit of recognizing them quickly, which is why we have example 5 on the back. So going through this, you could pinpoint and pick out how these things are congruent to each other and if they are. So we're going to determine whether a pair of triangles can be proven congruent by using theorems that we have learned. If so, write a congruent statement and identify which theorem was used. With this example for A, we know that WP is congruent to XZ. We know that WA is congruent to XY. And we also know that PA is congruent to ZY, which leads me to SSS, being my theorem showing that these triangles are congruent with each other. Great. With this, I know that SQ is congruent to WT. I know that QR is congruent to TU. And I know my angle R is congruent to angle U. This shows SSS, yes, congruent. This shows SSA, which means no congruency. No congruent triangles. I guess be a little more formal. No congruent triangles. For C, I know that I have VX being congruent to XZ, and I know that VY is congruent to YZ. One thing that I also can say is that XY is congruent to XY because of the reflexive property, which means that this is congruent by side, side, side. So yes, triangle congruency. Yes, we have congruent triangles here. We're gonna skip D for a second. I gotta do some mental gymnastics for that. For E, we have that TW is congruent to QS. We know that RS is congruent to ZW. And we know that angle R is congruent to angle Z. This is congruent this is our hypotenuse-like theorem because we have right angles. These are our right triangles. So this is our hypotenuse-like because this is SSA, and that means that, yes, these triangles are congruent for D. So D is a tricky one. Yes, we have congruency here with angle K being congruent to angle M. We have that angle P is congruent to angle N. And we can also prove that angle L is congruent to, well, we can prove that angle KLP is congruent to NLN by vertical angles. So this is something that we haven't even touched upon yet in class, which is angle, angle, angle. 5.6 is when we talk about like angle congruencies, or like how to prove triangles with angles. This is angle, angle, angle. And this means, foreshadowing, that no triangle congruency. Angle, angle, angle is a case like SSA, where we can have some congruent parts, but it might not mean the triangles are fully congruent. You can have these angles be completely like the same. Like, let's go down here. Think of equilateral triangles actually for D. Like, think of that. That's an equilateral triangle. We know that. Let's just say the sides are 5, 5, 5. Cool. And we know the insides are 60. We also have this. This is also an equilateral triangle. It has angles on the inside, all meaning 60, and the sides are 25. This shares the same, this is angle, angle, angle. They have the same angles on the inside. Everything is 60 on the inside. All angles are 60 degrees. They're all congruent to each other. So that's good. We know that. But the sides are not equal to each other. So angle, angle, angle is not valid. We can't use that to prove congruency all the time. Just like an SSA. We can't use that for proving congruency all the time. But we'll touch more on that in 5.6. Do your proofs. Just like a regular problem. Don't worry about the proofs. The proof section right away. Worry about figuring it out as like a normal problem. I think that's going to help you guys the most. Instead of worrying about the 2-column and this, worry about this first, getting like the actual triangle congruency part. Explain your reasoning too, like work your way through it as well. And then worry about like just lining everything up. That's what I did in example 1, and in example 2, and in example 4. So I think that's your best bet of being able to do proofs. I'm going to be honest, because proofs are still tricky, but hopefully you'll get the wraps of it on Tuesday, because we're going to be doing stuff with proofs. So yeah.